So we'll now compare the Riemann and Lebesgue integrals. So on the real line R, we have two integrations. So one is Riemann integration, and there is the Lebesgue integration. First is the Riemann integral defined. So Riemann integral f bounded on AB finite interval. And if it exists, you call it integral a to b f of x dx. This is the notation for the Riemann integral. Now if you want to to extend to unbounded functions or infinite intervals, you may have suitable limit processes. And the integral may or may not exist. The Lebesgue integral, on the other hand, is defined for all non-negative measurable functions and integrable functions. And the integral can be finite or infinite. If it is finite, we say it is Lebesgue integrable, of course. The Lebesgue integrable is denoted by integral f dm1 over the set E on which you are integrating. Now, for instance, we have seen in the earlier that there exists sequence of Riemann integrable functions whose limit may not be Riemann integrable. On the other hand, so the typical example of this is the characteristic function of Q intersection 0, 1. So this is Riemann integrable, this is not Riemann integrable. On the hand, this is in fact the characteristic function of a countable set, and the Lebesgue integral is just a measure of the countable set, which is 0. So, but integral chi q intersection 0, 1 dm1 equal to 0, right? So it exists. Okay, so we have this. Now we ask the question that if you have a bounded function which is Riemann integrable, is it also Lebesgue integrable? And if so, are the two integrals equal? Well, for the health of the theory, it better be so, because if you have two different methods of integration and you get different results, that's a very uncomfortable situation, and it is not good. So we have to. So we will now show that if you have a bounded function, so bounded function on AB finite interval, Riemann integrable implies Lebesgue integrable, and both integrals coincide. So this is what the question which we want to ask, and we hope that the answer will be affirmative. Okay, so let us proceed. So how do you define, so AB finite interval in R, and then P is a partition. So P is equal to A equals x naught less than x1 less than xn equal to B. So this is a partition. So the points xi, I equals 0 to n, are called the nodes of P, the nodes of the partition. Okay, so some finite number. Then delta P, which is the max of 1 less or equal to I less than equal to n of xi minus 1, the interval lengths, the maximum length of the subintervals is called the mesh size of P. So a partition P dash is said to be a refinement of P if the nodes of P are contained in the nodes of P dash. So you have a partition here. So this is a partition P. Now I add to it the midpoints of these intervals. So then you get, and then you retain the old nodes also. So that will be a new partition, and this will be obviously a refinement. That means the intervals will become smaller, and therefore this is a finer partition, and so it's called a refinement of the thing. So now let f from AB to R be a bounded function. Consider Pk, k equals 1 to infinity, sequence of partitions of AB such that 1, for every k, Pk plus 1 is a refinement of Pk. For instance, we refine this. Now you add the midpoints of each of these subintervals and so on, you get another refinement of the previous one. So like this you can proceed to get more and more finer and finer partitions. Okay, and 2, but you should do that so all over the place. You should not do just in some places and leave the others. So the condition is delta Pk tends to 0 as k tends to infinity. So now if Pk, this is bad notation because I am not bringing in the k, but anyway it doesn't matter because I am not going to use the nodes, less than x1 less than xn equal to b. So recall that n will be nk. Okay, there will be points will be there. So this is the partition Pk. So we define uk to be the function f of a plus sigma k I equals 1 to n of mi chi of xi minus 1 comma xi closed, and Lk equals f of a plus sigma I equals 1 to n small mi of chi xi minus 1 xi, where mi is the inf of f of t belonging to xi minus 1 xi, and capital Mi is the sup of f of t belonging to xi minus 1 xi. Okay. Then if you recall the definition of the of Riemann integration, you have the upper Darboux sum and lower Darboux sum. So this is U of pk f, this is L of pk f. So what is this equal to? This is equal to sigma I equals 1 to n mi into xi minus 1, and this will be equal to sigma I equals 1 to n small mi xi minus 1. And if you, in the language of Lebesgue integration, this is nothing but integral of uk dm1 over ab, and this is the integral over ab of lk dm. Now pk plus 1 refinement of pk for every k. So what does that imply? That implies that L1 of x is less than or equal to L2 of x is less than or equal to f of x, which is less than or equal to u2 of x less than or equal to u1 of x. Because you are taking the supremum over smaller intervals, so the supremum will be less, and here you are taking infimum over smaller intervals, so the infimum will be more. So that is why L2 is bigger than L1, U2 bigger than U1, and in general for every k you will have this inequality here. Okay. So theorem f AB to R bounded Riemann integrable function, then f is Lebesgue integrable and integral a to b f of x dx equals integral over ab f dm1, that is the two integrals are the same. So we are going to use, so proof with above notations. You have uk x n equals 1 to infinity is increasing, it's a decreasing sequence bounded below, and Lk of x k is an increasing sequence bounded above, hence convergent, both are convergent. So let us take the limit. So Lk of x goes to L of x and uk of x goes to u of x. Then this implies that L of x is less than or equal to f of x less than or equal to u of x from this condition here. Also f bounded, this implies integral u1 dm1 over ab is finite. Therefore we can ask, dominated convergence theorem can be used, and this shows that integral over ab uk dm1 will converge to integral over ab of u dm1, and integral over ab lk dm1 will converge to integral over ab L dm1. Now f is Riemann integrable, so I am using all the hypotheses. So you have that the upper and lower dark bosoms converge to the Riemann integral. Therefore, what does that mean? That means integral a to b f of x dx equals the limit of the uk, so that's equal to integral u dm1 over ab equals integral over ab L dm1. But also u is integrable because f is okay, and therefore you also have that but u is become equal to L. Okay, so these two integrals are equal, implies that u of x equal to L of x almost everywhere, because we have shown a non-negative function, if the integral is 0, then it's equal to 0 almost everywhere. We have proved that proposition. So u minus L is a non-negative function and the integral is 0 because of this condition here, and therefore u equals L equals x almost everywhere. That is because f lies between u and L, you have that ux equals fx equals Lx almost everywhere. So this means f is equal to u or L almost everywhere. That one f is Lebesgue integrable, and integral f ab dm1 equals integral u ab dm1 equals integral L ab dm1, and that's equal to integral a to b f of x dx, and therefore f is Lebesgue integrable and the Riemann and Lebesgue integrals are equal. So that proves this theorem. So next important theorem, which almost follows from this, f ab to r bounded function, then f is Riemann integrable if and only if f is continuous almost everywhere. Okay, so we have seen that means except on a set of measures 0, f is continuous. Now we have already seen, you might have seen in your master's course or course on rail analysis, that if a bounded function has at most countable number of discontinuities, then it is Riemann integrable. Now here this is a generalization of that result. We say a countable set is a measure 0. So you can have a function which is discontinuous at a set on a set of measure 0, otherwise it's continuous, then also the function is Riemann integrable. So we recover an old theorem in a slightly more general form. Proof. Okay, so again use preceding notations. So assume x in AB is not a node of any pk. Okay, so now nodes of pk are finite. So union over k nodes of pk is countable, hence measure 0. So we are taking x outside this set of measure 0, and now you have f is continuous at x if and only if ux equals fx equals lx. Because what are ul and all that? uk comes from the maximum. So look at the definitions of these things, uk, lk, and definitions of mi and mi. So you have that uk and lk converge to u and l, and therefore here, and therefore you have this condition here. Now if you have continuity, then these three will be same, and if these three are same, then obviously the function is continuous also. So you have that f is continuous at a point x if and only if u equals f equals lx almost everywhere. Now from proof of preceding theorem, if f Riemann integrable, this implies u equals f equals L almost everywhere, that is f is continuous almost everywhere. Okay. Now conversely, f bounded and continuous almost everywhere. This implies that u equals f equal to L almost everywhere. So this means that since integral uk converges to u and integral lk converges to L, integral L, so those two integrals are equal, and consequently given epsilon, this is less than epsilon for all k sufficiently large, and that is one of the conditions for Riemann integrability, that is mod u pk f minus L pkf is less than epsilon k large, and that is implies f is Riemann integrable. One of the criteria, one of the alternative definitions of Riemann integrability is that given any sequence of partitions you have, that you can do this. Okay, so this proves, so we have proved that if a function is Riemann integrable if and only if it is continuous almost everywhere, and if it is Riemann integrable and bounded, then its Lebesgue integral is the same as the Riemann integral. Very good. And all this was done in a finite interval AB. So example, not true if interval is infinite. Because here we are going to define the Riemann integral in terms of some suitable limit processes. Okay, so let us give an example. Let us take 0 infinity contained in R, and you let f of t, f of x equals sin x by x. I should put x not equal to 0, but as x goes to 0 the limit is 1, and therefore this function can be taken up. So this is a standard exercise in contour integration. You can look at any complex analysis book, so All-Force for instance. F is Riemann integrable on 0 infinity, and integral 0 to infinity f of x dx, this well known, is equal to pi by 2. But f is not Lebesgue integrable. So we want to show that f is not Lebesgue integrable. So we have In to be the intervals n pi plus pi by 4, n pi plus pi by 2, n in n. So these are all disjoint intervals. On In, you have mod sin x is bigger than or equal, because it's n pi plus pi by 4, so mod sin x will be bigger than 1 over root 2, and mod x will be less or equal to 2n plus 1 pi by 2. That you already have here because it's in that interval. Mod x is the same as x, okay, on In. So for x in In, we have mod of sin x by x is greater than or equal to root 2 by pi into 1 by 2 to the 2n plus 1. So if you will consider the integral over 0 infinity mod f x mod f d mu dm1, this is greater than or equal to the n equals 1 to infinity integral of In mod f dm1, which is greater than or equal to sigma 1 over 2 root 2 sigma n equals 1 to infinity 1 by 2n plus 1. The length of these, in each interval it's this, length of the interval is pi by 4, and therefore from that you get the pi goes away and you get a 2 root 2 at the bottom. Okay, so now this is a divergent series, and therefore you have integral mod f dm1 over 0 infinity has to be plus infinity. So f is not Lebesgue integrable, and therefore. Okay, so now the next thing we will do is to see a couple of instances of how we use this fact about Riemann and Lebesgue integrals being the same for bounded functions on bounded intervals, and use that to study the integrability of functions on the real line, and then also try to compute those integrals.